Let's discuss an important topic now: how to reduce labeling effort. To train machine learning models, especially deep learning models, we need a lot of training instances, and this can be quite expensive even with crowdsourcing. And this is especially the case if the crowdsourcing task is a complex one. Now let me motivate the problem a bit using a real example, one of the expensive crowdsourcing experiments I have done. On the slide is a task that we did at Amazon. The goal here is to find out between two products that are comparable in terms of functionality. For example, here both are headsets. Which one is higher quality and why? We present information about the two products, including the seller's description of each product, and under that, lists of product-related information provided by customers, including question answers and reviews. To the right are the phrases extracted from both seller and customer information, which crowd workers use to characterize the criteria for the quality judgment. For this task, it takes 12 minutes to compare 5 product pairs, which cost about $2. We asked the workers to judge 1,000 pairs, each annotated by 10 workers. Overall, it costs $5,000. You can see that this is a very costly task, $5,000 to get only 10,000 product pairs annotated. And if you think about it, this is not a lot to train a neural network. If we can reduce the number of labels needed to train a machine learning model, we can actually save a lot. Here is another example that do not directly involve crowd workers, but the implication of reducing labeling effort is even bigger. This work was done when I was an intern in the Alexa team. I assume that you all know Alexa. It's a personal assistant AI technology that is used in many voice devices that helps control, for example, lights, microwaves, oven through voice. Another important use case is to place an order, so users can make a purchase through voice. Now, very roughly, the way Alexa works is that it first converts customer voice to text and then use all kinds of natural language processing techniques to understand the customer queries. Among those techniques, a very important one is intent classification, that is, identifying whether or not customers have shopping intents. This might sound a simple task, but it is not. It is because, well, first of all, the queries can be very ambiguous. For example, when someone asks Alexa, "Can you find me an iPhone?" we don't know if the user wants to buy an iPhone or she just loses her iPhone at home and asks if Alexa knows where it is. Also, intents are contextual. Some queries issued in the morning might indicate very different intents from when it's issued in the night. Considering this, who are the best annotators? The users themselves, right? There are no better annotators than the users themselves. Ideally, to train an intent classifier, we can use Alexa to collect directly the labels from customers by asking, for example, "Do you want to shop?" Occasionally doing that is fine, but if Alexa constantly asks that kind of question, you know what will happen? Well, people will not use it anymore. So we desperately want to minimize the number of questions asked without sacrificing model performance. But what can we do to reduce worker effort and the cost? Well, one thing that we need to keep in mind is that it's the labels that are costly to obtain, but usually it is very easy to get access to a large amount of unlabeled data. For example, documents of the web, speech samples, images, and videos. The idea of most methods for reducing worker effort is to leverage the unlabeled data to make data labeling more efficient for model training. And to do that, there are two main approaches: active learning and pattern labeling. In the following, we will focus more on active learning, which has been extensively studied, and briefly talk about the more recent idea of pattern labeling. Let's look at active learning. The key intuition of active learning is that a machine learning model can achieve greater accuracy with fewer training instances if it is allowed to choose the data from which it learns the best. To illustrate this, on the slide you can see three figures. The left one shows instances of two classes. The one in the middle shows the decision boundary of a linear model that is trained on 30 randomly selected instances. The accuracy in this case is 70%, as you can see. And on the right hand, you can see the decision boundary of a linear model that is trained on 30 actively selected instances. The accuracy is 90%. You can see that if we allow the model to actively choose the most informative instances for model training, the model can reach good performance even with a small number of training instances. As an implication, we don't really need to have all the instances labeled, but only those selected by the model. And by doing so, we can largely reduce data annotation work and hence the cost. Active learning generally works in cycles. We train an initial model with a small number of instances in the labeled training set, then apply the model to the unlabeled set to select data instances for labeling. We then ask humans to label the instances and inject the newly labeled instance into the training set to retrain a better version of the model. Note that this is the most common setting of active learning. There are other scenarios as well. For example, in a streaming setting where instances come at high speed, the model will not select from an unlabeled pool of instances, but rather to decide whether to request the label of new instance or simply discard it. There wouldn't be another chance for the model to see the exact same data instance again.